Hi, this is Solomon. We are in the third part of the six-part series talking about 6 questions innovative thinker would ask. We talk about space and time. Now we are going to talk about what? About matter and also about energy. Lately, we're very excited about the James Webb telescope that can see much deeper into the universe, farther away and also more in the distant past. It's better large because it got a bigger surface area to catch more light, as well as it can catch the infrared spectrum that is more dominant in the early universe. This is the Big Bang as seen over time and also over space. Now this Big Bang occurred here, and there's a very rapidly increasing universe called inflation period, where the expansion speed of the universe is faster than the speed of light. And then later on it slowed down into the dark ages when all matter in the universe is ionized and therefore no light can propagate through. And then as it go on, the universe keep expanding, not as fast as in the inflation period, and then star beginning to form, and then galaxy begin to form, and then about 14 billion years we have right now. This is the cross-section of space. You can see the galaxies here and also strings of galaxies deeper into the past. And so one thing that we are going to talk about today, besides matter and energy, we are also going to talk about dark matter and also dark energy. Now this is peering into almost the beginning of the universe, less than 1 billion years since the Big Bang. What you can see here are very old galaxies, probably less than a few hundred million years old, and they are more reddish in color, largely because the universe at that time is expanding so fast, and they are kind of moving away from us at a very high speed, so the light becomes redshifted. Now what you saw in the earlier picture is not just matter but also energy. And here I'm going to prove to you E equal to mc squared. And you can generate matter from a accelerator here, the Large Hadron Collider in Switzerland and France. Now what you can see here are basically you have opposite directed proton beams that is accelerated round and round in a large circle, and at one point they would collide with each other. So the kinetic energy of these colliding proton stream, called Hadron Collider, would generate a lot of particles, and the energy used to accelerate this particle is turned into matter. The proof of E equal to mc squared is quite simple, different from what is given by Einstein. Now, Newton's formula is F equal to ma. If you modify Newton's formula, instead of F equal to ma, what you can do is that the ma is the rate of change of momentum, which is mass times velocity with respect to time. Now, what we're going to show here is that as the velocity approaches the speed of light, you can pull the v outside, so it's c times the delta of m. Now we're assuming that as you put more energy into the accelerating particle, they would increase in mass of delta m. All right, so now if you multiply both sides by the distance moved by the particle, the distance delta t is c times delta t, because you're close to the speed of light. And so you will have F times c delta t here, which is the energy E that would be used to form new mass delta m. So what you have is that if you multiply this side also by c delta t, it cancels out the delta t. What you have is delta m times c squared. So that's how you get the E is equal to delta m times c squared here, and therefore the amount of energy that you put in to the system accelerating particle is converted into mass. And so you have this equivalence of energy and mass, E equal to mc squared. This is one of the biggest galaxies that you can see in the universe. It has a massive center as well as a lot of star formation on the outside. Now, galaxy not only show us the visible matter all around, but also it shows us there's a lot of dark matter in the universe. Why are there dark matter? If you look at the revolution of matter around the galaxy center, you find that they are spinning at a speed that is much faster than it would be if the galaxies hold back together by the gravity of the visible matter, including the black hole. The reason is that they speculate that there is a lot of dark matter that is spatially evenly distributed, and that allow the galaxy to rotate at a much higher speed than otherwise would be for the galaxy to fly apart. This is a picture of what we call gravity lensing. What you have is that there could be a very bright object because there's a black hole or a lot of dark matter in this area. The light coming from this very bright object would turn around and allow us to see fringes so that light is somehow bent as it comes to us on Earth. Now, this also illustrates that the turning, the lensing effect is much more than what we can see here, the amount of mass that we can see here. And therefore, there is a lot of dark matter. For that matter, I think we know that the visible matter in the universe is around 5% of all the mass of the universe. And then there's about 5 times more dark matter, about 25% or slightly less than that is due to dark matter. So both visible matter and dark matter account for less than 30% of the mass of the universe. Then what else are there in the universe? Now, this is a picture of somewhere in our galaxy, Milky Way galaxy, whereby these are not dust, but these are gas that eventually form stars within this gas cluster. So this is a huge amount of gas. And the reason why we can see it much better using the James Webb is because these gas, such as methane or hydrogen and oxygen, emit light more in the infrared region, and they travel to us, and we can see them much better with the infrared telescope that James Webb is. Here, if you look at the detail within that massive amount of gas and dust, you will see star formation, practically gravity allowing the mass to come together and then being compressed and then ignited to form helium from hydrogen. So you have formation of new star that you can see very clearly here. Besides dark matter and ordinary matter, we lately discovered there's a lot of dark energy. Now, how do we know there's dark energy? We know that because when we look deeper in the universe, we find the farther away it is, not only is receding from us at a higher velocity, it's increasing, it's accelerating its expansion. So when it's kind of like an explosion, we would know that there's energy that caused the explosion and the expansion in the volume of the universe. Now, how do we measure that? Now, in the 1990s, what they use are these so-called standard models or standard candles that you can use to measure both the distance as well as the velocity of these standard candles. Now, these standard candles are very bright supernova, and they're standard candle largely because they emit about the same luminosity. And so if that is farther away from you, and you can measure the amount of light collected, then the farther it is away from you, the less light you will collect, and therefore you know that it's very distant from you. How do you measure the velocity? You measure the redshift of the light that you collect from this supernova explosion. So from there, you derive both the receding velocity and also the distance of that supernova from where you are. Okay, and to our surprise, that the redshift as a function of the distance away from us is not just linear, but it's accelerating. So which means that the farther away from us, the thing actually is accelerating in its expansion, and therefore we conclude that there's a lot of dark energy. Now, finally, I would like to describe a little bit about the nature of energy. Now, nobody knows what energy really is. We know that energy is conserved, and energy can convert it into matter when it's up. For example, we accelerate the particles in the super collider, and then they collide together. There will be a lot of mass being generated. We really don't know what energy is, other than the fact that mass converts to energy. But I can speculate a little bit. For example, if you talk about gravitational field are basically curvature in space and time. So I can speculate that curvature of space-time actually is energy. Now, you can also derive that conclusion from observing a black hole. Now, this is a reason about 2 years ago, we were able to literally take a picture of a black hole in Messier 74 that we shown earlier. It's a massive black hole, billions of times heavier than the black hole in the center of our galaxy. Now, that is very far away, but what you see here is that as matter falls into the black hole, it emits radiation. Now, I would like to tell you again, you may say that space is what you can see. Well, that's not quite true. If you talk about a black hole inside here, there's no space inside there because light cannot travel inside a black hole. So therefore, you have space all around, but there's absolutely no space inside a black hole, okay? So space practically collapses on you. It's not even a hole. So what you have here is that the light from behind the black hole, and I'm just shaping it like this, the light will come and being bent around to the front side, and therefore you see this annulus here. It's because of light bending from behind to the front. All right. Now you think about a spinning black hole as having matter falling into the center. So there is an annulus of light that is coming out, very much like the rings of Saturn, that is from the back, because the back side, the light will come out here, and then you will see this structure. And sometimes you can see a flare that's coming out on either side because of that ring structure of matter falling into the black hole. Now, lately we also found a much smaller black hole inside the Milky Way galaxy around the Sagittarius area. Now, again, I would say energy comes from fields, and you can have a gravitational field, or you can have the electromagnetic field. All right. So I think what fields are basically curvature in space and time. In gravitational field, it's the curvature in the three-dimensional space and time, and quite possibly electromagnetic force could be curvature in high-dimensional space and time. But that's purely speculation. So I would say we have to understand matter from the point of view of space and time. And I think energy comes from curvature of space and time, and therefore matter is a crystallization of energy as the temperature cools down, they form particles. We know a lot more about matter. We know a little bit less about energy, but we know enough to really talk about what's the matter with energy. And this is a book that I've written, and you can download an online version of the book or read it online for that matter from our website, solomon.ac. I hope you can learn more about energy and how it interacts with energy. Now, I spent a lot of time thinking about energy, largely because I want to solve the most major problems that we are encountering these days. First, the lack of energy, and second, the lack of environmental protection, and third, the lack of good education for innovation. So I wrote this book for these 3 E of energy, environment, and education, and I hope that you can think what's the matter with energy, and to help solve the energy crisis and the environmental crisis that we face nowadays. Until next time, this is Solomon.